All right. Good news is we officially now have everybody who's got me added as a person on Colab. So you should see if your stuff wasn't graded, it's all graded now. All right. Um, what were we doing last time? Been a long weekend. Assignment, turn keyword, function, boolean, equivalence, blah, blah. All right. So last time I think we were I talked about some index of function and what the equivalent is um, in Python. And kind of what's good about this little discussion. Oh, just the guy there. Um, is that from the very first week of class, I made some comment along the lines of, programming is the skill set, the language does not matter. I mean, so these little stupid string functions in Python, I have a recollection of the last time I used it or whatever, but every language has a tool like that. Search through a string, find the first occurrence of something, return a -1 if it wasn't there. Use that logic to solve whatever problem you're solving. The programming language itself does not matter to accomplish that stuff. I'm going to go ahead. I'll just start. Actually, I'll do it in the um, same thing as we were working on last time. So just to give you this real quick. Well, I'll leave that there. So let me just give an example of that fine thing so we can see it. So I'm going to say S is equal to hello. We're going to say print S dot find and H. You run this, make sure it does what it's supposed to do. So this should give me a 0. There's the 0. If I say give me an E, this should give me a 1. Let's do multiples of these. So E should give me a 1. L should give me a 2, the first occurrence of that guy. And Z, for example, should give me a -1, not found in there. So there's my 0, 1, 2, -1. So the equivalent in Python of Java's index of function is a string function called find. We'll use it by some examples here.
How do you find the second occurrence?
There are some functions that will find the last occurrence.
Okay.
If you want to find the second occurrence, you'd have to search for it. So, I mean, it's an interesting question. Let's actually think about that. So let's think we want to find the second L, the location of the second L in a function. Go ahead. Okay. Well, I like where this is going. It wasn't where I was going, but it's a good place to go. So let's talk strings. So strings are collections of chars. Kind of already talked about that. They are an object type typically built into the language. And that actually makes it a little bit tough, especially in Java. So I would say Java, well, you already know my feelings on Python. It's a ridiculously terrible language, but not that but it's an important language. I mean, it's kind of like we can sit here and rip on Microsoft and say, oh, Microsoft stuff is all junk or whatever, but a zillion people use Microsoft stuff, so get used to it. The punchline. Python is probably the most popular programming language right now. If you just went pound for pound, the number of people who use that as a programming language, you have a huge group of, let's call them real programmers that are transitioning over from other languages because Python's kind of where all the libraries are for AI stuff, things like that, a lot of data science stuff. And then you have people who are in kind of like programming adjacent careers, whether it's data science, like actuarial science, things like that, where you're working with a lot of data sets and you're visualizing and stuff. And you're not really a coder, but you need to know enough to be dangerous. It's kind of the reason why we use Python in this class now is because we have some other majors here at the university who rely on coding one to give them enough exposure to programming skills to do what they need to do in their daily job. So, while I might say from a, real programmer's perspective that I don't appreciate some of the flexibility Python has, it probably helps a lot of people do their job more easily rather than having to get into the weeds with what I think are better languages like C, C++, Java, even C Sharp. But, whatever. But in any case, every single programming language will have a string data type. Just like we talked about all those primitive types that every single programming language has, and they all came from C. So all of our modern programming languages, I don't care if they're compiled or interpreted or whatever, they took humongous influences from the C programming language from the 1970s. That's where it all comes from. All right, so anything that has little deviations from it isn't going that far from the apple tree. All right, you can use your knowledge of older languages to directly apply to this. And strings are a good example. So, and strings are probably our most problematic object across programming languages. We'll keep talking about this. So let me add a slide here. Primitive types versus object types. All right, now we've looked at our primitive types. So in generic languages, it's byte, short, int, long, char, float, double, and Boolean. Some concoction of those. Some newer languages kind of meld all the integer types together into just a single, I'm a whole number thing, and then it just kind of handles, the size things behind the scenes. All char types use Unicode, or older languages will use ASCII behind the scenes. All Booleans are trues and falses. Most modern languages like Python probably does have a way of depicting something as specifically being a float. Because I think I had mentioned an older language like C or C++ supports both floats and doubles. Remind me, what's the difference between a float and a double?
How large it is.
How much space it can hold. So a float is kind of like an int, where a double is kind of like a long. So a float is a, 16 bits before the decimal point, and it's 32 bits before the decimal point, 16 bits after the decimal point. So 48 bits is the physical size of a float, and a double is 64 bits before the decimal point and 32 after the decimal point for more precision, has a bigger footprint. Most of our more modern languages will just they'll treat it as a double, the bigger version of that, and just kind of behind the scenes figure out memory. But most of our modern languages will have a way of specifically saying whether something needs to be treated as a float. A lot of times you'll put a little F after it or something like that. That goes back to some of the early graphics packages for doing GUI stuff, GUIs. It needed to be in a very specific format, so you still have to work with some of those things. But these are just kind of outliers that when you're working on a language and you're dealing with floating point numbers and you need to make sure they're treated like floating point numbers, you have a way of saying, treat this like a float, not like a double. So when you get into that, you can do it. So primitive types are built into the language and can only hold a value. All right, so I want you to think about these variable type things as kind of what's their talents. So a primitive type like an int, it can only store a value. It can't do any other stuff. I kind of like teaching this from the Java perspective. So we're going to swing back on that here in a second, but that's okay since the language doesn't matter. Object types can hold one or more values and potentially do more. This. I want. It's not just Java. All object types can hold one or more, can hold 0 or more values. It can also do other stuff. And I'll give you an example of that. I just want to open up get the Java documentation going here. Well, here, let's just do this. That should get me right to it. All right. I'm going to come back to the screen in a second. Just want to get it up. All right. So object types can choose to hold values that they want, but they can also potentially do other things. So for example, strings can report their length. Strings can give you a character for a particular place in the string. Give me the char that lives at bucket 1. So out here in Python, where's my super ninja? So if I were to print out S at bucket 2, that's going to go to my string S, which is this guy. It's 0 index, that's bucket 0, bucket 1, bucket 2. That's going to give me this L. So if I run this, this shows me the L. If I want to have it not look so much like L1, let's change this to bucket 4. That'll give me my O. Ay, ay, ay. So there's my O. So I can access individual buckets of a string using this little bracket format, which comes from the C programming language for something called arrays, collections of stuff. If you're in Java, you actually don't work with strings using that same syntax. You instead have a function called char at, which guess what? Gives you the character at a particular position. Does the same thing. All right. So right off the bat, if I have an int, so if I have int a is equal to 5, for example, or if I'm in Python, I just say a equals 5, because we don't have strongly typed situations there. All a can do is hold a value. That's the end of its talents. It can't do anything else. This is built into the language, and its only job is to store a piece of data. Whereas object types, if I say string s is equal to hello, I can say s dot length. In Java, I think in Python, print s dot. I don't think it's, well, let me try it. I know it's len is the function you can send it to it, but I think there's a built-in thing. No, so I have to pass it len, so it's actually not a built-in function. So if I want the length of a, oh my gosh, why isn't it clicking in here? I hate this keyboard. Well, it's not broken. It's just I'm not used to it. So if I say, give me the length of S, we've already see this work. That gives me the 5. So that's actually not really the example I'm talking about here. That's another function that's operating on a string. But we did see that if I say s.find, find is a function that is owned by the string class. The string object has at least one additional ability where it can give you the place in it where it first found a particular character, or a -1 if it didn't. It has an additional ability. Go ahead.
Back to that slide. So what would you call, I guess the dot, like, would you call that a method?
Method, function, subroutine, procedure, any of those is correct. The object-oriented thing would be method.
Okay.
So if we go way back in time in the early programming languages, they were all called subroutines. Then we had a division where we called some functions and some procedures. Functions were subroutines that returned a value. Procedures were subroutines that didn't return a value. Once we went object-oriented, we started calling them methods, I guess just because. So methods either have a return type or don't. So we've now remerged functions and procedures together into something called methods. Doesn't matter what you call it. It's a reusable chunk of code that, or a chunk of code that you can call multiple times. Somebody else wrote it in this case. So for us in Python, we would say s dot find like an E, and that would give us a 1 for this one because that's the location where that E is first found.
Methods.
Yeah, synonyms.
Yeah, methods mainly for Java functions.
Object-oriented languages. Yeah, the word method was associated with object-oriented languages when they first came out. I think it was Smalltalk, I think was the first language that introduced that phrase, but they all mean the identical thing. So if anybody ever says, people don't really say subroutines anymore, but if anybody ever says function, procedure, method, they're talking about the exact same thing. Either you wrote the function that you're calling or somebody else wrote the function that you're now using. All right. So at the high level here, what we want to keep in our mind is that we have two different types that live in programming languages. We have the built-in types that can only hold stuff. That's it. They allow us to remember a value, but can't do extra stuff to operate on it. And then we have another type that can hold stuff if we want it to. So for instance, strings hold a collection of chars, but we can write our own object, maybe for a player, and we're going to be doing this soon enough. Or let's say we want to create a program that creates a list of players on a baseball team. And maybe we're going to keep track of that player's first name, last name, and jersey number. So now we're going to hold 3 different pieces of information inside of an object, 2 strings and an int, for example. But we could also have an object just called my object that doesn't actually hold any information. It just does stuff. That's legal as well. So we don't actually have to hold a value inside of an object if we don't want to. We can just have it perform things, and we'll see that by example when we get into it. But for us in here, I want us to think of like objects as kind of being like super versions of variables, you know, more powerful. And that comes with some additional complexities. So objects typically are stored in a memory address. So we actually have pointers that we're working with when we're dealing with objects. So now we get those hexadecimal memory addresses that freak us out. We go running off, all that stuff going on. But I mentioned that strings, we're going to say problem with strings. Strings are almost always the first object programmers learn, because human beings, we do a lot of stuff with words, right? So kind of makes sense. And the people who made these programming languages know that. So they said, you know what? If the programmers are going to be working with strings often, let's go ahead and make strings convenient to use. Seems nice enough of them, right? But let me reword that sentence. Let's go ahead and make strings behave differently than every single other object. So to teach about generic objects through strings as our first example is actually a horrible thing, because strings don't behave like normal objects. They behave differently because they're basically a primitive type, but not. Something along those lines. Now, let me show you some evidence of this built into the documentation of a programming language. One of the things we're going to learn in here is we're going to get very good at being able to look at code and look at documentation and being able to immediately use it. Programming is not about memorizing all the things in a language. If you use a language often enough and you have your subset of these 15 functions that I use all the time, you're going to accidentally memorize those things. It's just going to happen. But we always have documentation we can refer to on any test or quiz in here. If I want you to use a certain thing, I'll tell you about it. I'll say, here's a function that does whatever. Sometimes I'll make up a function on a test and says there exists this function that does X, Y, and Z. That way, if you're doing it online, ChatGPT is not going to help you. So I guess I've never heard of this function. It'll just make something up. All right. But let me give you an example here. So I'm going to say strings behave differently than every other object. So we're just going to say that this is a bad first example of an object, even though it's almost always our very first example. All right, so now when I go into the Java documentation here, and I'm only using Java's documentation because I would say Java has the strongest documentation of all languages. In fact, it was actually a feature of Java when it first came out. They called it JavaDoc. And the idea was that, as a programmer, you don't even have to put comments into your programs or anything to explain what's going on. You just use our special JavaDoc format. In the end, you run this program and it will generate pages that look just like this. So if I go into this class, it'll give you the name of the class. It'll give you, here's the fields for it. Here's the constructors. Here's all the methods. All this stuff is really easy to read. That's great. One problem. Programmers didn't put the JavaDoc stuff into their programs, so it didn't matter if we had this nice tool that self-documented all your code. Programmers are generally lazy and we minimize the extra stuff we put into our code. So it didn't work out, but it's an easy thing to show stuff for. All right, now what I want to show here is when we talked about primitive types, and I've already said it once today, but we talked about things like bytes, shorts, ints, longs, floats, doubles, chars, booleans. These are our core things. Notice here, I'm looking at the class library for Java here. This is in java.lang. So this is the core Java language that comes with Java out of the box without you doing any extra stuff. Python will have equivalents to this kind of stuff, but the documentation here is much stronger. Notice we have a class here. So whenever you hear the word class, think objects. Classes are objects. They're the blueprints that describe how an object works. In this case, we're seeing these are objects that were already built into the system by Sun Microsystems, who is now called Oracle. Notice we have a class here called Boolean. Well, we've heard of Booleans before, right? It's one of our primitive types. We have one called byte, one called character, one called double, one called float, one called integer, one called long, one called short. Yeah, these are all class names. So punchline is we're noticing that there exists in Java a class for every single one of our primitive types. Why do you think that is? Remind me, what's a primitive type? Yeah. Built into the language, can only hold a value. That's all it can ever do. Now, might you want to do something to integers? Maybe convert a int into a string, convert a string into its int equivalent. Might we want to do something to chars? Maybe convert a lowercase character to an uppercase character, stuff like that. Okay, so we might want to do things with these primitive types that they can't do to themselves because they're only primitive types. Therefore, it would make sense for programming languages to have these like kind of factories that sit here. It's like, okay, we've built this thing called integer. So if you want to do stuff to ints because they can't do it themselves, just throw us an int and we'll take care of it for you. It'll do all those things. If I click on integer here, and we just flip through, we see we can get the bit count, we can get the byte value, we can compare two ints to each other, we can get a double value of an int, so it converts it to a double, a float value. We can get a hash code, which is what's called a one-way cipher. We can get the minimum and maximum of two integers. That's kind of built in. That's not a humongous major thing, but what if I asked you, back to our code here. Lost, I'm always lost. Okay. So if we have A is equal to 5 or 4, and we have B is equal to 7, and I want to know the maximum value of those two things, how would I want to print to the screen the bigger value of A and B. What could I write? We just ask a question, right?
Okay,
If A is greater than B, print A. That'll be the maximum value. Else, print B. This will display the maximum value of those two. If they're both the same value, it doesn't matter which one we display. All right, so that's not a humongous amount of code for us to write to accomplish this. Now, keep in mind that this only works in this example right here. But if I wanted to write my own max function, where I can pass it two integers and it will return for me the larger of the two. For example, we wrote a function the other day, this guy up here called char to digit. So we defined a function. Here is its name. Here's the inputs it requires to work, and here's all the logic. So I can do another one. I can say def maxint A and B are two integers. If A is greater than B, return A. Who? No, I'm not. We're good. I'll show you here in a second. Else, return B. I have this guy minimized. I'm just kind of getting it out of the way. So kind of forget that that guy's even there. So here's a function right here called maxint. So I've decided, you know what? It's going to be handy in my program here to be able to quickly throw two integers at something and have it spit back the larger of the two. Maybe that's handy, right? So sure, I showed you it's built into most languages. Most programming languages will have like a math library that does a whole bunch of stuff like that. All right, but it's not a huge deal. We can write that little function. Again, I know right now, all of you should be struggling on your assignments. It looks like things are going pretty well. You're spending 3 or 4 hours to write less code than that, which is fine. That's exactly where you should be right now. But when you see it written, it should make sense to you. All right. So now what I can do down here is I have my two integers. I have my hard-coded logic, but then I can also say max int AB. Both of these should print out the same thing. I have 5 and 7 are my two integers. I asked the hard-coded question, if A is larger than B, if 5 is greater than 7, print out A. That's not a true statement, so we'll fall to the else. We'll print out B. B is a 7. We wrote that identical logic inside of our thing called maxint. It's going to give us the same thing. It's just going to boil down to a 7. Except now I wrote it one time. I can call that whenever I need the maximum value of two numbers. So I should get a 7 out of both of these. If I change max int, I just pass it two different numbers. It'll give me the larger of those two numbers, which is that guy. So functions are things that either are built into the language or things that we can write ourselves that we can call over and over and over again. So sometimes if we have something that we imagine we might do several times as we're working through our program, maybe I need to get a maximum value of two integers often. If it's not built into the language, or you decide, I'm not going to go and waste my time looking for it built into this language. Instead, I'll just write it in 4 lines of code and move on with life. Doesn't matter if it was already one built in. You can just do that. All right. So functions are convenience things for us. If we were going to have a rule of thumb, go back right after the primitive type slide here. Rule of thumb. Use variables when you need to use a value more than once, or if there is value in labeling a value so it is clear what it represents. So, for instance, maybe if you're only going to use your age once, it might still make sense for you to have a variable called age, set it equal to 25, and now you know that that random number 25 represents an age. Sometimes labeling it inside of a variable, even if you're only going to ever use it once, can make sense. But as a general rule of thumb, when do we use variables? When you're going to use the value more than one time. That way you're not hard coding it in 2 different places. Because if you then decide you're going to change the value, you have to go and change it in 2 places, as opposed to if you put it in a variable, you only have to change that one variable, and then you use the variable in those multiple places. Another rule of thumb. Write a function to accomplish a logical task that you might call upon more than once. Now, if it's something that's very particular to the exact problem you're solving and you're in the middle of writing a function, and you can say, okay, well, I can go and write another function that solves this problem, or I can just put the 3 lines of code in here, and I'm never going to do that. I'm never going to use this for any other part of my program. Don't just create another function for the sake of creating another function. When you look at your program, when all is said and done, and that's kind of why in these integrated development environments like this, we have the ability to kind of minimize our functions. So at the top of your code, even though this guy might have 5,000 lines in it, for example, this guy might have 40 lines in it, we can have them all collapse down to 1 line. So it's not muddying the waters or whatever. All right. So you don't want to have, well, when you look at your code at the top here, for example, let's assume you put all your functions at the top of your code. That's usually good programming practice. Let me finish this thought and I'll talk about why that is here in a second. You want to be able to look up there and kind of see all of the useful abilities that you've written into your program. You don't want to see a bunch of useful abilities and then a whole lot of kind of these one-off little halvesy abilities that happen to be used by just one of those functions or something like that. It's just going to muddy the water. You want your code to be fairly self-documenting, so only put things into functions that really need to live in a function. And ultimately, this isn't even a programming concept. This is an organizational concept, right? Sometimes you put stuff away in drawers to make it look all neat and stuff. Other times you might not put it into a drawer because you use it every 15 minutes, and if it goes into that drawer, you're never going to find it again, right? We use our own common sense, and sometimes my wife doesn't agree with my choices. All right, we're talking about something else now. I did get back at her this weekend though. All right, so let me it's actually a funny story. So if you're interested, ask me after class. It's actually related. Somebody was asking me about um oh, let's just tell it. All right, so um how many of you know what a Messianic Jew is? All right, that's what I am. So my whole family is Jewish. I have cousins who are rabbis. My dad's one of 7 brothers, all doctors and lawyers. The whole stereotype is a thing. All right, my brother and I are both Christian, but Messianic Jew sounds cooler, right? Now, what's funny is, it's kind of this ongoing. Well, the funny thing that happened years ago that I was referencing. I don't remember who I was talking to. Was it Carson or was it you? About the funny Jewish story. Was that you? All right, so years ago, I was in the Holy Land with my church. We were in the old city of Jerusalem. We were at the Wailing Wall, the Western Wall, and just to the left of the Western Wall is this thing they call the Holy of Holies. So you have to be male, and you have to be of Jewish descent to go there. Now, I'm on this trip with a whole bunch of like my Christian church, right? And I'm like, okay, well, I have my documents, so I'm gonna get everything together. I got dual citizenship, the whole rigmarole. I was born in Kentucky. It's not like I was born over there, but you pass it down through the lineage, right? So I'm waiting in line. You got these military police checking everybody. This dude points at me and just waves me in on the nose. He saw the schnoz and he said, "This guy's good." Wave me in. So, what's funny is my wife. You've seen those DNA tests that you can do that kind of show you like where your people came from, where all the different things, and usually you have like my wife might be part German, part French, part 30 other things, right? So she's thinking, apparently she looked up that most people who would identify as being of Jewish heritage are usually between like 40 and 60% Jewish. It's like midnight on Saturday, and I'm asleep. And she wakes me up and says, "Oh my gosh, you're a pure Jew." 100%. Nothing separated for it. So it was funny. So I guess we assume I'm always right. So, anyways, that was the funny thing this weekend. Probably funnier to me than some of you, but there's 40 years of inside joke that's been traveled along. But I have photographs of exactly where my people apparently came from. All right. So we got off on that tangent, but it was a good one. Let's see, primitive types. Rule of thumb for why functions are usually at the top. Good programming practice typically will have people writing all their functions at the top of their program. And then the rest of the program after that, once we get into bigger programs, I'll start structuring them. Python lets you get away with not structuring your program quite like a typical program, but we're going to get into the habit of writing our code using something called main, and we'll see that here shortly. But the real question is in programming, like in most things in life, we have different rules of thumb that we kind of learn over time, or there's certain things that are considered best practices. Sometimes it's just because somebody said it's a good idea. Other times there's real rationale behind it. Does anybody happen to know why functions are typically written at the beginning of your programs with the logic that uses those functions later on? Go ahead. All right, so tell me more about that. You're saying he says so you can call them later on. You're on to something decent there.
Well, because I know like whatever.
Okay, so we have something a little bit of a chicken or the egg problem, right? You can't, if you're on line 5 and you try to call a function that you don't write until line 80, it might not know what you're talking about, right? Good.
Programming languages, the ones that run as you go, you have to define it first because you use it later on, but if it's compiled first, it can be anywhere because it has it already.
Sort of. Okay, so he added some good stuff. So interpreted languages, said non-compiled, languages that don't run off of a compiler, they run off of an interpreter. They move through your program from top to bottom, typically, so that anything you want them to be able to know about, they need to run into first before you start calling upon them. It actually isn't 100% true anymore for the same reason we're going to be talking about the compile side of things. In the early days, so we have this idea of a compiler. So compilers are associated with typically strongly typed languages. These guys convert between a high level language and a low level language. We saw this. That's all a compiler does. This guy converts from a high level language, so Python, Java, C++, etc., to a low level language like assembly. And we saw some examples of that. That's what a compiler does. Now, over the years, compilers have gotten better and better and better. One interesting thing you see in the programming world is that new interpreted languages come out every week, it seems like. There's 4 zillion different interpreted languages. So you have some that have bubbled to the top as having a whole lot of support, Python being one of them. Node.js is actually a JavaScript super library that lets you do front end and back end programs, but that's become very popular. But then you have a zillion different programming languages that were invented by random people that just never took off. Okay, but a programming language only has to support remembering things, asking questions, and repetition, right? There's nothing that special about a programming language. Now, in the early days of compilers, we had something called single pass compilers. So a single pass compiler ran through your program from beginning to end and executed, well, and created executable code along the way. Executable low-level code along the way. In that example, if you had your functions later on in your program and you tried to call them higher up in your program, it would say, I've never heard of this thing, because it was trying to do everything in a single pass. Years later, we had multi-pass compilers. This ran through your program once and collected all the introduced symbols, like variables, functions, etc. Then it would make a second pass and would convert the program to executable code. So if you are writing code today for like a modern C++ compiler, you would not need to put all your functions at the top. It would technically work if you put your functions strewn about your program as long as they were in legal places. All right, because modern compilers are multi-pass compilers. So a lot of what we're seeing here is left over from yesteryear, let's say. Now, out of curiosity, and the expectation is the answer could be 0. How many people in here have coded in either C or C++? All right, you've worked with header files. All right, but you've seen the .h files? The top, well, in a C++ program here, just if I say I want to create a new file, or whatever, let's call it that, and I switch that to oh, it doesn't give me a yeah, there we go. So here's a C hello world program. Top here, it's including standard IO.h. So it's a header file is what these are called. And I'm going to swing back onto this once we start writing our own objects. So I'm kind of giving you some foreshadowing type stuff, if you want to think about this like a novel. So the way this worked in older programs is they would define the functions inside of a separate file, this header file, so that you can now just include that at the top of your program. So your program didn't have 4,000 lines of code sitting at the top. It had a single include this header file, and that header file had the 4,000 lines of code in it. Good. Actually, let's say the answer to that is yes. So for the online people, he asks, is that why in Java you typically put stuff in separate files? Java doesn't have header files. Java, similar to how I've mentioned that Java is kind of C++++, where it took away a lot of the things that the programmer used to have to do, but they always did it the same way. Java just said, look, we're going to handle that for you. So now when you put certain stuff in one file, usually in Java, you have a whole bunch of files that are called classes, and then you have one file. In fact, let me actually get this out there. I've referenced it several times today. And it's an important thing. Sort of, but Java fixed something. I'm just going to put this in here. All programs begin and end with main. And I'm going to swing back onto this, but we see the evidence right here. We have this thing called main right here. If I change the language up here to C++, we still have, oh, what did I do? We still have main. If I change this to Java, we still have main. We still have a main method right here. Main is everywhere in every programming language except Python. So, but Python has main. If I switch this to Python 3, I think that's pretty close to the syntax.
It needs to be like underscore main.
Oh, is it underscore main?
Yeah. Well, it's still in quotes though.
We could just look it up here real quick. There we go. All right, so although you know what, I don't even think that is quite getting it right yet.
But then that as what calls the main.
Yeah. Main in Python. If name is equal to this guy. Oh, so it is pretty much what I ended up having. That's fine. So moving forward, I'm going to write all our Python programs with that in there. So really, I could put a whole bunch of stuff before that. I'm just going to copy that and I'm going to go back to my projects, go into test. So what we would oh my gosh, I hate this. The whole thing, everything about this is just, I don't like it. So we go back in here. My program kind of starts right here. I would write this like this. And then put everything inside of that indented. Gosh. So you usually would have your program with a bunch of functions in it, and then at the very end, you'd have main. And main is actually where your program actually begins and starts doing its stuff. All right. So this idea of all programs beginning and ending with main is this truth. And it actually is true in Python. Python just allows you to start writing scripts on a single page because Python started off as just a scripting language. And now it's been used to solve much more complex programs, including big websites or backends to websites, things like that. So almost every single one of those you'll see now will have the structure of having one file with a main in it that says this is where the ball is hiked. You know, if we want to think about it. And main ends up saying, okay, call this function, create this variable, call this other function, which maybe calls 10 other functions, but ultimately comes back to main. All right. So main is kind of our centerpiece with that. All right. And we're going to see lots of examples. I just wanted to get that out there because that is a truth across programming languages. Programs begin and end with main. And this idea of having these header files at the top was our way of making our programs less messy. You know, you wouldn't have just one file with 10,000 lines of code in it. You could have 10 different source code files with all the details kind of hidden. And then at the top of your program, you would just include 5 header files or something like that. Java allowed you to put your stuff into 10 different files, but it didn't actually make you import all the header files. It just says, look, as long as they're in the same package, for us, let's just think about that same directory, you could just call them and we'll find them. Not a hard thing for computers to do. Now, there is a little catch here, though. Say problem. What happens when two functions, we can say 2 or more functions, rely on each other? So if you have function A that calls function B, and function B that calls function A, which order do you define them in? Because each one is reliant on the guy that's coming after it. So you can never find, you know, one of these is going to fail. The one you write first that calls the second one, it's going to say, I've never heard of that guy. Before we had 2 multi-pass compilers. All right. So does that mean that when we had single pass compilers, when it literally started at the top of your program and just started walking down and it hit function A, and function A talked about function B, and you hadn't hit function B yet? Does it mean you just could not do that? You could not have 2 functions that referred to each other? What do you think? Well, first of all, what's your gut feeling? Do you think that was just something you couldn't do? Or do you think there probably was a way of pulling it off?
It probably would.
All right. Now, in modern languages, it just works. It's like, look, this is something that's going to be kind of common. We realize you're going to write functions. They might be dependent on each other. We'll just go and search everything and we'll figure out what you're talking about. And when you've been ambiguous, we'll give you an error and then you can go fix it. But as long as you haven't been ambiguous, as long as you didn't write, you don't have 2 functions with the same name in 2 different files and we don't know which one you're talking about, we'll do the work for you. But before we had multi-pass compilers, how was this problem solved? So I mentioned last class, or maybe 2 classes ago, whatever it was, the show MacGyver. We solve problems in terms of the tools that are in front of us. And so the way this worked is what we would have inside our header files. So let's say you had a header file, and really you can think of a header file as being equivalent to just having all that code right at the top of the file. When you say import blah, blah, blah .h at runtime, it literally inserts the contents of that header file into the top of your file. All right, so this is really for human visibility only at the end of the day. But inside those header files, what you'd have is at the top, they would be prototypes. So they would have the very top line of every one of the functions, not its implementation. It would say, there will be a function called function A. I'll define it later. I'll give the logic of how it works later, but I'm telling you it will exist right here. The next line down, there will be a function called function B. I'll tell you about how it works later. So now function A and function B are now known about by the compiler, even though they haven't started calling upon each other yet because their actual implementation is later on in the code. Okay, so we got around this through something called prototyping. These were all very good lessons for beginning programmers. This is why I typically would teach C++ as the first programming language, but I'm still making the connection back because these are truths regardless of the programming language. Python just hides so much from you because it tries to be very convenient for modern programmers, which is great until you need to solve a problem that is weird and now you don't have the background that you needed to solve it because it's based on something that, hey, this is this library, especially with video games or something. The libraries we use for video games, many of them are left over from like the 80s or 90s. You know, because they're just physics engines that say, okay, you want to do gravity? Gravity means that when something's falling out of the sky and it has this mass, we can figure out how fast it's falling over some period of time. You had it in high school physics, and it's just a math problem. Somebody else wrote it. The math hasn't changed, so why rewrite it? It's fine the way it is. All right. Back in here. So we're going to say in the old days, we prototyped functions where we mentioned them by name early and then implemented them later in the program. And we'll see examples of how this works. All right. So let's get back to this idea of primitive types versus object types and how Java or how strings are among the worst objects to learn first, but it's also the best object to learn first because it's the objects we're going to see a need for strings much earlier on as beginning programmers and the types of things we might want to automate than we will any of these other kinds of objects. All right, so our next challenge that we want to do that will use strings. So a string is a collection of chars. They're an object type built into the language. They behave largely like primitive types, except when they don't. And this is where kind of experience comes in. Messing with it, manipulating it, things like that. All right, so now we're going to start messing with strings by an example. So we've already written some code that converts a string representation of a number in some base to its decimal equivalent. That was our implementation of one of our patterns, right? All right, now our other pattern was, what if you start off with a decimal number and you want to convert that to a base? Now, if we look at our program we've written so far, notice that, oh, and this question mark thing was left over from our issue last time, but notice here that our initial value is represented as a string. We then went and did some magic. We got our answer built up as an int. We spit out the answer. Now, if we were then to take that answer, which is the decimal equivalent to whatever's an initial value, and we say, okay, now let's convert it back to whatever base it was in, the solution is probably going to be a string. We're going to take it from a number back to a string. All right, so let's look at this guy real quick. Let me get rid of those things. Let me make sure this guy's Where have I indented in a way that has a
Wild.
Oh, thank you.
Print. Well,
No, yeah, the prints, yeah, thank you. So there's our 2989. All right, so our final answer here was 2989 in decimal. So now if I wanted to, and we started off with what, base 16? So I said, here's our starting value, BAD. We're saying this is represented in base 16, so it should be made up of 0 through 9, A through F. We're going to convert this guy to decimal. All this code goes and converts that to decimal. In fact, we can take all this logic and let's put it into a function, def base to decimal. And we're going to call this guy, this is going to take in an initial value. And I pasted all my logic in here. It probably should also take in the base. So I give it the value and the base. It goes and does all the magic. And in the end, it'll return answer. All right, so identical logic that we already wrote. I've just squeezed it all into this function, took two of the variables that we were working with, put it into the inputs of the function, and say, if you give me these two values, I can do the rest of it for you. And then return your answer. All right, kicker. So if I now call upon base to decimal, passing it BAD and 16, what should the output of my program be? Say it again. Okay, nope. It was meant to be a trick. So the output of this program is nothing. Why is it nothing?
nothing.
Printing and returning values, two different things. Super important. It's something beginning programmers have trouble wrapping their mind around, even though it's a simple concept, which is why we're using a simple example. All right. So printing versus returning. Functions will often do something and then return the result for some other part of the program to do something with, including possibly printing it, right? Printing just displays whatever we wanted to print to the screen for human eyes to see. So in our case right here, I am calling my function base to decimal. I am giving it its two inputs. I'm giving it the initial value, and I'm also telling it the base that initial value is in. This guy's going and doing all of its magic, doing all the conversion, yada, yada, yada. In the end, it is returning the final answer. It's returning it. And what am I doing with the thing that's returned here? I'm doing nothing with it. Just wasted my time. Well, what if I say the answer is equal to that? What will the output of this program be now? Still nothing. I've done something with it, but what I did with it is I stored it into a variable. If I want to actually reveal this answer to the end user, I'm going to have to finally print it. All right. So I could have printed it directly if I wanted to, or I can just print out the answer that came out of there. Show you a separate example of this. All right, so now I'm calling my base to decimal again, passing it a different value that I've written using a bunch of zeros and ones, and then I've advertised that this guy is actually a binary number because this technically is a legal decimal number, right? In fact, it's a legal everything number. This can be any base, so we really do need to say what base it was in, even though we might look at that and suspect it's probably a binary number if you use that many zeros and ones together. We get our two different answers there. So notice in the second one here, I am taking the value that is returned by base to decimal, and I am immediately printing it. I am not storing it anywhere. So after line 50 here, I have now lost that value. I can't do anything else with it. Whereas I can do something else with the answer. I can just print it a second time, let's say. So I've stored my result up here on line 48. When I converted BAD from base 16 to decimal, I've stored it. And now I'm going to use that variable for other things. I can do math with it. I can display it. I can do whatever I want because I remembered it. Now I can use it. All right. So we should see 2989 a second time. All right. Questions about any of that before we go and write our other pattern? Okay. So $29.89 from decimal to hex. We want to write a program that accomplishes this task. We've learned both patterns. We can do them by hand. We went and we implemented the other pattern. So now we have code that can convert any base to decimal, right? As long as it fits within base 36, fits in the alphabet. All right. And there's nothing that says we can't go beyond that. We just have to start making up our own rules of what's representing the next base. All right, but 2989, this is the other pattern we want to do. This is the one where we divide over and over and over again. So 2989 divided by 16, because it's in hex. 2989 divided by 16 is 186. And this is going to be a remainder of 13. So if you do 186 times 16, it'll be 13 short of that thing. 186 divided by 16 is 116. Did I type something wrong? Oh, thank you. 186 divided by 16 is 11. That's a remainder of 10. 10 divided by 16 is 0. 16 goes into 11 0 times with a remainder of 11. All right, now, in our last minute here, we've teed this up for next class. What we're doing here is we just solved the problem, reminded ourselves how this pattern works. Some things should be standing out to us right now. We're like, you know what? Every single time I do this pattern, I stop when I get to a 0 here. I repeat something over and over and over again until something is a 0. Sounds a lot like a loop, sounds a lot like a Boolean expression for that loop. All right. Then in the end, we read our answer from bottom up. So this is an 11, a 10, and a 13. And we would then map those things to a B, an A, and a D. Now let's write the code. All right, so next class, we're going to come back. We're going to implement this function. I would challenge you before class to try to write this yourself using what we've done so far. You don't have to hand it in or anything, just see if you can challenge yourself to do this generically using the code that we've already written. And what I'll do here is I'll share this link. Huh?
That's being bad.
Yeah, that's what that map does. So here I put that link to the current code on that slide.
Oh, that's on, yeah.
All right, I'll see everybody on Thursday.
Oh, yeah, you didn't complete your. Oh, yeah, yeah. Still thinking, and I have like. To do. Yeah, I'm curious because like.